So welcome back to part 2 of this video on Kummer extensions. So we're now going to prove that if you have a cyclic extension of degree n of a base field which contains a primitive nth root of unity, that is necessarily a Kummer extension. But before we do that, let me just make a comment, which is that Kummer extensions, according to our original definition, i.e. you take a base field with a primitive nth root of unity and you take the splitting field of a polynomial of the form x to the n minus a, where that's an irreducible polynomial in the ring of polynomials over the ground field f, we showed that they are simple extensions achieved by joining on a single root of that polynomial x to the n minus a. And therefore, they are all simple radical extensions because that element that you're joining on, it is a radical, it's an nth root of a. So that's just the first comment that I wanted to make, that Kummer extensions are all simple radical extensions. So now let's do the proof that I was talking about. So we've got our field f, our base field f, and our top field k, and the base field f contains a primitive nth root of unity, and this extension is a cyclic extension of degree n, so that means it's a Galois extension with Galois groups Cn. And I want to now show that this is necessarily a Kummer extension. Now, I warned at the end of the previous video that I'm going to pull a rabbit out of a hat, and this is where I'm going to pull that out. So I am going to, well actually firstly, let me just make a comment about what linear characters are. So we are going to use a little bit of character theory here. Don't worry, only basic character theory, only degree 1 character theory. And I'll try and prove the actual result that we're going to use from linear character theory, which is the linear independence of characters, or the linear independence of degree 1 / linear characters. So firstly, let me just tell you what a character is. So if you've got a group G, and you've got some field F, then if you have a group automorphism, let's call it sigma, in fact I might put it here, sigma, which maps G onto the multiplicative group of F, then such an such a homomorphism, I hope I said homomorphism. If I said automorphism, I apologise. So let me start again, because I can't remember whether I actually used the wrong word. So if you've got a homomorphism, a group homomorphism from a group G, which could be finite or it could be infinite, into the multiplicative group of a field, then such a group homomorphism is called a linear F character. And you can, if you like, replace the linear with degree 1. So a linear or a degree 1 F character of G. So that's the definition of a linear character, and it comes from character theory, which is a big part of representation theory. In representation theory, you know, there are higher degree characters. But we won't get into what they are at all. We don't need them here at all. You don't need to understand anything about higher degree characters to understand what we're going to use here. We're just talking about degree 1 characters. So, the reason this is relevant to us is that all the elements of the Galois group of K over F, so if I have sigma, which is an element of that Galois group, if you consider the multiplicative group of K, then that is being mapped into the multiplicative group of K. So this is actually a linear K character of K star. So I can put in the F here, the field is K, and the group is K star. So it's a linear K character of K star. All of the field automorphisms that are in the Galois group, they are linear K characters of K cross. And this is because, you know, the only element that's not in K cross is 0, but 0 is being mapped onto 0 itself. So everything that's non-zero is going to be mapped onto non-zero. Nothing that's non-zero is going to be mapped onto zero. One, because it would violate injectivity of an automorphism, and two, because it would violate those of the algebraic. Well, actually, no, it wouldn't violate those of the algebraic properties. Ignore what I've just said. It would violate injectivity of the field automorphism. So field automorphisms have to be bijective maps. Zero is being mapped onto zero by the field automorphism, and therefore nothing else can be mapped onto zero. So we know, therefore, that if we restrict down to k cross, it will be being mapped onto k cross, and it will actually be still a bijective map from k cross to k cross. But it does satisfy this definition of being a linear k character of k star, or k cross. Fine. Now, there is a fact about linear characters, that if you have loads of them, and indeed all of the different field automorphisms, they're all going to be in the Galois group, they're all going to be different linear k characters of k star. The fact that we're going to use is that they are linearly independent, they're k linearly independent. So let me just explain this. So if you consider the set of all maps from k cross to k, and you know, these maps here that I've got, these k characters of k cross, they are all maps from k cross into k. Now you might say but aren't they going into k cross rather than k? Well, yes, but k cross sits inside k, so they are actually all maps from k cross to k. You know, it's nothing fancy is happening here. But if you consider this set of all maps, this means all functions. This is the set containing all functions that map k cross into k, all put into one great big set. This forms a k linear space. It forms a k vector space, because you can add any two functions together just by the reason it forms a k vector space is because the domain is a field k. So you can add any two functions together. So if you want to add the two of them together, it will be defined by it maps any x onto whatever f1 mapped x onto, and then you add what f2 mapped x onto. So that's the definition of how you add two functions together to get another function that will map k cross into k. And similarly, you can scalar multiply. So if lambda is an element of k, then lambda times f, it'll be defined as the function that maps x onto whatever f mapped x onto, and then you just multiply it by lambda. So the obvious definitions of how to define a scalar multiplication, a k scalar multiplication, and how to define addition. And then, of course, you need to check that this satisfies the definition of a vector space. I'm not going to do that. It's all simple. There's nothing complicated, I don't think, in this. And this is a well-recognized fact, that spaces of functions from any set, and you could have replaced this with any set you like here, and indeed actually the sort of the finite dimensional k vector spaces, so k to the n, you can see that as the space of maps from the set of n things, 1, 2, all the way up to n, into k. That's another way of viewing those finite dimensional vector spaces. So now all we're doing is potentially allowing the set to be infinite, potentially uncountably infinite even, potentially in the case of this k cross. So you can stick whatever set you like here for k cross, or indeed in place of the set 1 to n, and it still remains a k linear space. So the set of all maps from k cross to k is a k linear space. Now, these field automorphisms that we've got in the Galois group of k over f, we've discussed how they are all linear k characters of k cross. They are all going to sit inside this vector space, and the claim is that they are linearly independent inside that vector space. So you cannot take a k-linear combination of them, a non-trivial k-linear combination of them, and get the zero map. So zero in this vector space will be the map that maps everything onto zero. So all the elements of k cross would be being mapped onto zero. Now, how do I prove that? So that this property is called the linear independence of linear characters. So if you want to Google this theorem, that's what you should Google, linear independence of linear characters. And it holds for linear characters of any group you like here. Yes, I think that is true, yes. So we'll prove it in the general case. So we'll prove it for general linear characters of some group. So let's say we've got some characters. So what should we call them? So generally the symbol chi is used for characters, so we'll use that. So if we've got chi1, chi2, all the way up to, let's say, and we're only going to have finitely many because the Galois group's finite, it's got cardinality n. So we'll have chi n, and they're all linear characters of G over the field F. So they all map G onto F, and they are group homomorphisms, and they're mapping G into the multiplicative group of F. That's how they're group homomorphisms. They're group homomorphisms with multiplication on this side. So why is it the case then that you cannot have a linear dependence? So why is it the case that you cannot have A1 chi1 plus A2 chi2 plus all the way up to an chi n equaling the zero map where the AIs are in the field F? So where I've defined what it means to add these characters and scalar multiply them up here, it means exactly what I've defined here when I was discussing why this is actually a K vector space. So in this case, K has been replaced by F, so this is an F vector space. These are all sitting inside this large vector space of all maps from G to F, which is an F vector space or an F linear space. I'll switch between using the word linear space and vector space. They're exactly the same thing. So all the characters sit inside here. They're very special maps, because not most of the maps in here are not going to be group homomorphisms from G onto the multiplicative group of F. So they're very special maps, but they are still maps inside this vector space. And I'm claiming that they are linearly independent. So there is no non-trivial linear combination that gives the zero map. So why is this the case? Well, suppose it wasn't true. Suppose there was a non-trivial linear dependence. Then you could pick the linear dependence that involves the fewest characters. So say I've got, and I'll do this without loss of generality because, I could relabel them up if necessary. So I'll assume that I have some linear dependence here which goes up to am chi m is equal to 0. So what I'm saying is all of these AIs are not equal to 0. They're elements of F that are not equal to 0. So this is a non-trivial linear combination. I've got rid of all the ones that have 0 as their coefficient. So the other ones, m plus 1, chi m plus 1, chi m plus 2, all the way up to chi n, we're assuming they have 0 in front of their coefficients. And I'm also assuming that this is the smallest such one, i.e. there is not a linear dependence, a non-trivial linear dependence that involves fewer characters than this, i.e. where even fewer of them have non-zero coefficients. So you can't, for example, find a linear dependence like this, A1 chi1, A2 chi2 is equal to 0, where only A1 and A2 are non-zero and all the other ones are 0. The M is the smallest such value that you can do this for. And as I say, I'm doing it without loss of generality. I'm just assuming that I've relabeled up, potentially, their indexes so that I've put them as the first M. Are the ones with the non-zero coefficients. So if there is a non-trivial linear combination that gives the zero map, then there will be this minimal non-trivial linear combination that gives the zero map. And now I'm going to get a contradiction because I'm going to show you that actually I can construct one that has even fewer characters appearing in it, which contradicts this being the minimal one. And therefore we've reached nonsense, and this therefore can't happen. How do we do this? So remember what this means. I'm having to remember how you do this as we go along, so bear with me a moment. So this means that for all G, for all little g is an element of G, big G, A1 chi 1 of G plus A2 chi 2 of G plus all the way up to am chi m of G, that it gives 0 for all G that you pick. Now, if I remember rightly, what you do next is you say, chi1 and chi2 are not the same map. They are different maps from G to F. So there therefore is some G0 where chi1 does not agree with chi2. So find some element of the group, call it G0, where chi1 and chi2 give different values. And this will exist because they are not the same map, so they cannot map every single element of the group onto the same thing. And therefore we know that A1, chi1, where do we go next? I think what we do now, if I remember rightly, is yes, this is how we do it. So we now say, if I multiply my general element G by G0, I'm still going to get some element of the group. So it's still the case that A1 chi1 G0G plus A2 chi2 G0G plus all the way up to AM chi M G0G, that is equal to 0. So, this held for all elements of the group. Whatever this comes out as, whatever you put in for little g here, this is still going to be some elements of the group, so this is still going to hold true. Good. Now what we can do is we can use the fact that chi1, chi2, all of the chi's are group homomorphisms, so we can split this into chi1 of G0, chi1 of G, and we can continue on, A2, chi2 of G0, chi2 of G, plus, and all the way down to AM chi m of G0, chi m of G. Good. That's equal to 0. And now here's the other thing that we can do. So we can, whatever G is equal to, so in fact this holds for all little g is an element of big G, and this one also holds for all little g is an element of G. So now I'm going to take number 1 up here, and I'm going to multiply it through by chi1 of G0. So you then get, if I multiply 1 through by chi1 of G0, I get A1 of chi1 of G0, chi1 of G, plus A2 chi1 of G0, everything's being multiplied by chi1 of G0, times chi2 of G, and then it goes all the way up to AM chi1 of G0, chi m of G. And that's going to equal 0. And again, this holds for all G. And now what I just do is I take this one here, and I subtract it from this one here. And of course, this term is going to go. This term cancels, and it's the only term. Well, it's not necessarily the only term that cancels, but you'll see what happens. So let's just write it out. So we get A2, and then we get chi2 of G0 minus chi1 of G0, and then chi2 of G, and then that carries on plus all the way up to, and then it gets to plus AM, and then again we've got chi m G0 minus chi1 of G0, and then times chi m of G is equal to 0. Now, I don't know, it might, by chance, some of these other coefficients here might come out as 0. It might just by chance happen that chi, some of the other chi's map G0 onto the same thing as chi1 does. But what I do know is I specifically chose G0 so that chi1 and chi2 do not map it onto the same thing. So I know that this does not equal 0 here. I also know that A2 does not equal 0. That was our starting assumption. Therefore, the coefficient of chi2 of G here is not equal to 0. So I've still got a non-trivial linear combination here of these characters that is giving 0. But what I found, this now involves one fewer character than my original one did. So I've actually found one that's even smaller than the original one, which by assumption was supposed to be the minimal one. So there's the contradiction. So that's why this cannot work. You cannot have a non-trivial linear combination of these characters that gives the zero map. Because if you did, you would be able to go through all such non-trivial linear combinations, find which one involves the fewest characters, but then you'd be able to do the argument that I've just done to contradict it being that minimum one, which is nonsense. So this is a contradiction, so this can't happen. So we therefore have that there are no non-trivial linear combinations of the characters which give the zero map. So now we're going to use that. So this then tells us that all of the elements of the Galois group, all of these field automorphisms, they are linearly independent in this set of maps from K cross to K. So that means that I can take a K linear combination of them and I know that it will not equal the zero map. So that's exactly what I'm going to now do. So my cyclic group Cn, let's say that it's generated by sigma, so it's a cyclic group, so it will have a generator. Let's call the generator sigma, and then all the other elements of it are just powers of sigma. So I'm now going to take this this K-linear combination of my elements of the Galois group. So I'm going to take sigma to the power of 0, which is the identity automorphism, and then I'm going to have plus, and then I'm going to have zeta n to the n minus 1, sigma 1. And by the way, this is the rabbit out of hat moment. This is where some genius spotted how to do this, and we're just going to use what they found. So then plus zeta n to the n minus 2 sigma squared, and you can see it's got a beautiful pattern to it. We're decreasing the power of the primitive nth root of unity and increasing the power of the sigmas, and you go all the way up to then you'll have zeta n sigma to the power of n minus 1. So consider this K-linear combination of the elements of the Galois group. So these are elements of the field K because they're all elements of the ground field F, so they're certainly elements of the much larger field K. So this is a valid K-linear combination of the linear characters, and what I now know is that this is not equal to the zero map. Now, why do I care to know that? Because it means that at the very least, some element of my group, so some element of K cross, so there will be some alpha in K cross, such that when I put it through this map, it does not give 0. And now I'm going to take such alpha. So I'm going to take this element in K cross, so some element of K that's not 0, put it through this, and I will get something that is non-zero. And in fact, I'm just wondering whether to change my... Oh no, we'll go with this. So we'll call this element beta. In fact, no, I am going to change over. I prefer to use alpha for this element. So I'm going to use beta for the element that I'm going to stick in, and I'm going to call the element that I get out alpha. So let alpha equal sigma 0 of beta. So I'm just sticking beta into this map, and I've defined how you define the sum and the scalar multiplication of these maps. So it's just you stick it into each of these maps and then add them together and scalar multiply. So it'll be sigma 0 of beta plus zeta n to the power of n minus 1, sigma 1 of beta, plus, and then it goes on, dot, 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 all the way up to zeta n, sigma to the n minus 1 of beta. And what I've said is I've chosen beta so that this is not equal to 0. So I now know that alpha is some non-zero element of my field K. Now, my next claim is going to be actually that this magic element alpha that I've constructed by a magic trick, that it actually generates the whole of K. So K is actually going to be F adjoin alpha. And moreover, it's going to turn out that the minimal polynomial for this is going to be one of those Kummer extension polynomials, and that's how we're going to show that this extension, this cyclic extension of degree n of a base field that contains a primitive nth root of unity, is in fact a Kummer extension. So in fact, just to revise what we've done so far, so we started off with this cyclic extension of degree n with primitive nth root of unity in the base field. We then said, okay, its Galois group has this element sigma as its generator, and then we took this magic K-linear combination of sigmas and we said, by the linear independence of characters, so by this thing that I've just proven to you from character theory, there must be some element in k-cross which, if I put it into here, gives me something non-zero. So do that now, take that element, put it through, and call the element out, you get alpha. And now I'm going to show that with this alpha, I can prove that this is actually a Kummer extension. So why is k equal to f adjoin alpha? Well, let's think about what the Galois conjugates of alpha would be. So we just need to think about what would sigma do to alpha. So if I put sigma and act it on alpha, so by the properties of field automorphisms, this is going to be sigma, and then I'm going to act it on this bit first. Well, firstly, so I'm going to obviously have to act it on the entire thing. So it would be sigma of all of this. But then I'm going to split it up, the additions split up, and then the multiplication split up as well. So I'm going to get sigma, and then it's going to be sigma of sigma 0 of beta. So that's going to become sigma 1 of beta. So that's that first term. Then now, if I act it on this second term here, so it's going to be plus sigma acting on the second term. So this splits into sigma of this bit here, this power of zeta n, times sigma of this bit. Now zeta n is in the base field, so therefore it's fixed by all of the elements of the Galois group. And zeta n to the power of n minus 1 is also in the base field, so it's fixed by all the elements of the Galois group. So I can pull that out, so it's unchanged. So it remains as zeta n to the power of n minus 1. And then sigma of sigma 1 of beta goes to sigma 2 of beta. And then carry on all the way up to the final one. Again, zeta n remains fixed, so it just becomes zeta n. And then sigma of sigma to the power of n minus 1 of beta is going to become sigma to the power of n beta, but sigma to the power of n is then the identity, so that's just going to become sigma 0 of beta. So what you can see is that this is the same element as we had originally, but now everything's been multiplied by zeta n, so this is just equal to zeta n times the original element alpha, because if I multiply this by zeta n, that makes that term there. If I multiply this one by zeta n, then zeta n to the power of n minus 1 times another zeta n becomes zeta n to the power of n, which is 1. So that becomes this term here, and then it goes on. You can see that that happens. And this is the magic. This is why we chose this magic linear combination of the sigmas, because this magic happens here. So sigma of alpha is going to be zeta n of alpha. So then what is sigma squared of alpha going to equal? Well, again, just act now sigma on zeta n of alpha, which is what sigma of alpha was. Zeta n is going to be fixed because it's in the ground field, so this just becomes zeta n times sigma of alpha, so it just becomes zeta n squared of alpha. And then by induction you can see that sigma I of alpha is going to map alpha onto zeta n to the I times alpha. So we see that alpha has n Galois conjugates in the field K. And since the field has degree K, it's clear then that the minimal polynomial for alpha is going to be degree n, and therefore this extension where you would join on alpha has to be the entirety of K because they have the same degree. But we'll go further. Let's actually construct the minimal polynomial for alpha. So the minimal polynomial for alpha by basic Galois theory, the foundations of Galois theory, is going to be x minus, and then we're going to have alpha, and then we need to put in all of its Galois conjugates, so it's going to be alpha minus zeta n alpha, and then x minus zeta n squared of alpha, and then all the way up to x minus zeta n to the n minus 1 alpha. So this is going to be the minimal polynomial for alpha over the base field f, which I'll denote like this. So m subscript alpha comma f, all of this bit in subscript, and then of x. So this is the minimal polynomial of alpha over f in the variable x. Now, divide both sides by alpha to the power of n. So if I divide this other side by alpha to the power of n, so I divide this one by alpha, I get 1 there. I'm going to split the division by the n lots of alpha. I'm going to give each one of these brackets a division by alpha, and that will overall then be dividing through by n lots of alpha. So again, it gets rid of that alpha there. Similarly here, we get rid of that alpha there. All the way up to this final one, we get rid of alpha there. So we have got overall n brackets, so we have divided through by alpha n n times. So this is what the minimal polynomial divided by alpha to the power of n is going to be. But then we recognize this polynomial. This is this has all of the nth roots of unity in. So this is going to be the polynomial x over alpha to the power of n minus 1. That's what that polynomial is going to split into over our field f. So, the polynomial, remember our base field f contains a primitive nth root of unity. So the polynomial x to the n minus 1, it will have as its roots all of the nth roots of unity, which will be x minus 1, x minus zeta n, all the way up to x minus zeta n to the n minus 1. So that's what we're using here. We're using the fact that we recognize this polynomial now. So this means that the minimal polynomial divided by alpha to the power of n is equal to this, and now just multiply back through by alpha to the n, and we get therefore that the minimal polynomial for alpha over f in the variable x is going to be x to the power of n minus alpha to the power of n. And because this is a minimal polynomial, this must be irreducible over the ring of polynomials over the field f, so in this set. And we've already argued that adjoining on alpha must give you the entirety of k. So what we've therefore seen is that actually k is going to be the splitting field over f of this irreducible polynomial, which is in f. So again, the minimal polynomial has to be in f. So whatever alpha to the n is, it's some element in f. So this polynomial does split in k, as we've seen. Once you've got alpha, you've got all of its, you've got alpha zeta n squared, etc. So this splitting field is equal to f adjoin alpha, and we've argued that f adjoin alpha is equal to k, so therefore k is equal to the splitting field of this. So we've therefore shown that starting with a cyclic extension of degree n where the base field contains a primitive nth root of unity, that we can then argue that that top field is actually the splitting field of an irreducible polynomial of the form x to the n minus some element of the ground field here. And that's the definition then of a Kummer extension. So such an extension is a Kummer extension. So there are now these two equivalent characterizations of Kummer extensions. You can either define it as it's the splitting field of a polynomial of the form x to the n minus a, which is an irreducible polynomial over the base field, where the base field already contains a primitive nth root of unity, or equivalently you can define it as a cyclic extension of degree n of a base field that contains a primitive nth root of unity. So we'll have a break here. In the final video, we'll just develop one final useful little theorem about Kummer extensions, and then we'll move on to cyclotomic extensions.